Hello and welcome to the Open Heat Transfer course Conduction. This course is brought to you by RWTH Aachen University and the University of Twente. My name is Wilco Rolfs, and in this video we will look at steady-state one-dimensional heat conduction with additional heat sources or sinks. What will we learn in this video? First of all, we look at the steady-state one-dimensional heat conduction equation with sources. What is a source? What is a heat sink? And then, based on that, we will derive the differential equation by use of an energy balance. In the next step, we look at the temperature profile, define the proper boundary conditions, and obtain a solution for the differential equation with, of course, these appropriate boundary conditions. Finally, at the end of the video, we will look at the generalized form of the temperature profile for different types of geometries, so a plane wall or a cylindrical wall or a sphere. This will give us a final differential equation that we can use in various aspects. What is a heat source, or how can we think of a heat source? So heat can be produced inside a body, for instance, due to an ohmic resistance if a current flows through the body itself. This is a typical example for a heater, or also inside the battery, but also there chemical processes are occurring and this increases the temperature. Also, fuel elements are classical examples for heat sources. What can be the reason for a heat sink? So if an endothermic reaction inside the body is taking place, for instance in a phase change material, those cases will lead to a reduction of thermal energy by an negative heat source that we call an heat sink. How is the heat flow of a source or sink expressed? So here in our lectures we always use the volumetric heat generation rate phi dot 3 dash. So the 3 dashes indicate that it's a volumetric source, and this source is then evenly distributed in the volume element V, but we can also think of a function where this is a function, for instance, of the radius itself. Now, looking at the units, we have here the heat flux and watt in the unit of watt, and this is equal to the volumetric heat source times the volume. So in other words, the volumetric heat source is the heat flux divided by the volume. And for the sink, we then introduce the negative sign, so that just means that the heat inside the volume is removed by the endothermic reaction. How can this look like if we would like to use our gut feeling to calculate or to determine the temperature profile inside such a body where uniform volumetric heat flux is occurring? So we have here two temperatures, T left and T right, and let's just assume these two temperatures are equal. Now, what is the course of the temperature profile? So for this we can first, of course, look at the differential equation. We have done this already in the first lectures here in this lecture series. So I think that on the left side we are sure that we look at the steady state condition, so there's a 0, and then the second derivative of the temperature with respect to space comes from the conduction inside the body, and then on the other side we have additionally the heat that is locally generated, so it's a d of the volumetric heat flux. The solution of this differential equation we have to integrate, of course, twice. And due to the two integrations, we have at the end here our volumetric heat flux associated with x squared plus then the known solution for the temperature profile if there is the heat flux is missing. So we have the C1 times x plus C2. So this will be a linear part here. And we see due to the parabolic and linear part, our equation here is of parabolic shape. The temperature decreases from the center location towards the outside, And if we make a test, if we just assume that the volumetric heat flux is equal to 0, then we come back to our classical linear profile of the temperature. So the equation seems to be consistent in terms of what happens if we remove the heat flux. Now we see here, if we look and draw this parabolic profile, we have an decreasing gradient. And why is this the case? Another idea or another approach, let's look at that. So we start here in this area. Let's see that this here is only part of the problem. So here is the line of symmetry. We have here a heat generated called Q1, and this heat that is generated in this first element needs to be conducted through this interface. So this interface of our control volume has then a heat flux Q conductive 1 is equal to the heat that is generated in this element. Now, if in the second element additional heat is generated, then the conductive part here, Q conductive 2, is equal to the sum of Q1 plus Q2. And we can follow this step further and further, and the heat flux increases. And you already see the solution here, that the conductive heat flux at the layer N is equal to the sum of the heat produced prior to this layer N. So this is then happening here at the latest part. Next question, why do we have a symmetry here? And that is, or vice versa, why do we have a zero gradient condition here at this location? And this is caused by symmetry. So due to symmetry, it's not allowed that there's a heat flux across any symmetry plane. And as there is no heat flux allowed, the temperature gradient needs to be 0. Let's now leave the Cartesian coordinates and go to the cylindrical body, in which we have now not only the effect of the volumetric heat source, but in addition the effect of the changing and increasing surface area due to the increasing radius. But not only the surface area increases, but also here the volume associated to the heat that is generated is also increasing. So we have to really take into account the area and the volume, and to calculate then the energy balance or the differential equation coming from the energy balance. So the energy balance is quite straightforward. We have an element here, or a control volume. There's a heat flux going in, there's a heat flux going out. We place them on the right side as fluxes, and then we have also inside this control volume the additional change of the heat source, or the additional heat that is introduced into our control volume. Now, the two heat fluxes by conduction, they can be calculated using Fourier's law, of course, for a cylinder, so the area is a function of the radius. The source term, we have to take into account that we have to use the heat flux that is generated here inside our control volume. So we have to make sure that this dV is equal to the volume here between those two dashed lines. And we can calculate this infinitesimal volume element by 2 pi r, which is then here the circle, and then times dr, which gives us an area. And of course, if we multiply it then with the length of the cylinder, we come up to a volume. Now we have defined all relevant quantities, and we can now insert them into the differential equation. So we start here with the energy balance. We use Taylor's series expansion to express the heat flux at location r plus dr. We see, of course, that this will cancel out in the next step, and we have to enter this dq source, of course, from what we have written before. So we come up here with this differential equation, And in this equation, we already see that 2 pi L is appearing in both on both sides. The dr is also appearing on both sides, very important. We know that this dr, this infinitesimal area or length element, needs to cancel out. And here, this is a differential with respect to r, and here we have another second differential. So crossing out all those terms, we end up here with the differential equation. We see if we cross out this part here, we are left with the traditional equation for heat conduction in a circular environment. But in addition, we obtain here this part, the volumetric heat flux, and we have put the thermal conductivity on the right side. So the next step would be to separate those parts. It's also possible, so we can have here the second differential of the radius plus 1 over r times the first differential with respect to the radius plus, again, the volumetric heat source. In the next step, of course, we want to solve this equation, and for that we need to look at the boundary conditions. We need, because it's a second order differential equation, 2 boundary conditions. So let's first start and look what happens here. What boundary conditions can be used and are appropriate. This cylinder has a symmetry around its axis, and thus the heat flux across the axis is 0, and of course this translates in a 0 gradient of the temperature derivative at r equal to 0. Now, on the outer side, we have to think about another boundary condition. So in general, one boundary condition would be to fix the temperature. So let's do that. We prescribe a temperature T1, and based on this prescribed temperature T1, of course, we can then calculate our parabolic profile. And what happens if the temperature T1 is increased? Then, of course, the heat is still transferred through this cylinder, and in the same manner as the temperature T1 increases, the temperature in the center of the body will also increase. The second case that we could imagine of is that we prescribe not the temperature T1, but we prescribe a temperature T ambient and relate the temperatures T1 and T ambient through the heat transfer coefficient alpha. So there is a relation between the heat flux that goes out of the body and the temperature difference T1 minus TA. So that's the equation. Of course, for the area that we have to account for is the circumferential area of the cylinder. And now we can calculate the temperature T1. Interestingly, we do not need to know the temperature profile inside the body to calculate the temperature difference between T1 and TA. Why is this the case? We know the total heat that is released by the cylindrical body as the integral of the heat flux Q dot 3 dash, and this integral is then Q dot 3 dash times the volume. And so if we are in steady state and the temperature does not change, the heat flux that is leaving the body, Q, is equal to the total heat produced inside the body. The outer part we can describe using the heat transfer coefficient and the temperature difference, and of course the surface of the body. And on the other side, this here is the volumetric heat source times the total volume of our body. And in this way, if we rearrange this, we can directly obtain the temperature, and then the temperature boundary condition of case 1 is very simple to the boundary condition of case 2 because we can directly prescribe a temperature, in this case T1. Now let's try to solve the differential equation. I've written again the differential equation here, but notice I have not separated this dr by separating the radius and the dt dr. This is not a really smart step to separate because it complicates the derivation of the equation and thus we stick here with this dr of r dt dr. Because now we can do the first integration of it, and in this step here we bring on the other side the r dt dr, and on the right side we bring the r, and if we do so we can integrate the part we are left here. On the left side we have r dt dr, and on the right side, because there was r already on the as a prefactor of this q dot 3 dash, here the integration of r leaves us or brings us to 1/2 r squared, and of course we have to account for first integration constant. We can use already this differential equation to calculate C1. Why? Because one of the boundary conditions is like the condition for the gradient. So we can utilize that at location r equal to 0, the temperature gradient dt dr is equal to 0. If we do so, we can directly notice that the constant C1 is equal to 0, which then reduces the equation because in the next step we can also remove one of the r, because here it's on the right side we have r squared, on the left side we have r, and we have simplified our differential equation that we can now in the next step integrate to the second time. So the second integration here, as you can see here, leads then again from r to r squared. Because there's already a prefactor of 1/2, this prefactor changes to 1/4, and in a similar manner we obtain a second integration constant. To calculate the second integration constant, we of course need to include our boundary condition, and let's assume that we have here this boundary condition where at the radius tr the temperature is the ambient temperature plus the radius times the volumetric heat source divided by 2 times the heat transfer coefficient. And if we do so, we can rearrange this and we obtain a second integration constant, which is depending on the temperature, and we directly see it's a linear depending on the temperature TA and of course on the heat flux that is generated inside the body. Now our equation with the entering the constant into the equation will finally yield us to the temperature profile with respect to the radius, and we see that it's again a parabolic profile because we have here a dependency on r squared, and this will bring us the highest order the parabolic type boundary condition. And interestingly, all the other parts here, they are not depending on r anymore. So here, of course, it depends on the outer radius, but there are no dependencies directly on the radius. The interesting part is if we compare the equation for the plate and for the cylinder, that they are quite similar. And this gives us the chance to create or develop a general temperature profile for the different types of objects, plate, cylinder, or spherical geometry. And we can see this here in the equation. So now the temperature, depending on zeta, which is a free parameter, is equal now to the TA plus another expression. And this expression depends then on two different variables, the variable s and the variable n. And these variables, they depend on the different geometries. So for instance, for the plate, our coordinate is the x coordinate and the parameter s is delta and n is 0. And if we replace now Sn and the parameter zeta, we can calculate the equation or obtain the equation for the plate. Note that the plate distance here is 1/2, or delta is 1/2 of the plate thickness. This is because of the symmetry condition. We see it here for the cylinder as well. We don't look at the diameter, we look at the radius, and so we can replace again all those variables with the radius, and then either with 1 or 2 depending if it's a cylinder or a sphere. But what does it tell us? That we can in all cases use the same equation, and especially because in all cases the equation here is of parabolic type. So this tells us that compared to a case where we just look at heat conduction and the profile changes from linear to a logarithmic style profile for the sphere, we have the similar temperature profile inside plate, cylinder and sphere, with of course the maximum in the center and then a decreasing parabolic distribution inside the body. Where is the largest temperature in our temperature profile? And for that we look at the maximum temperature. We can identify that because this part reduces the temperature. We can put the parameter to 0 and we see that the maximum temperature is at the center, and for the minimum temperature we have to increase this value to the maximum, so where those values here become 1 because the position is equal to S, and in this case here we obtain again a temperature for the outer surface, and this outer surface temperature is of course then the same as we have used in our boundary condition, where we calculated where we used the temperature at this location again as a boundary condition for the solution of the problem. Now if we look at this equation, we can also see that if we increase the heat transfer coefficient, of course the temperature decreases, and if we increase the volumetric heat flux, then of course the temperature increases. Now I'm at the end of the presentation. A few questions. So first of all, what is the temperature profile for cylindrical bodies with sources? The answer is that independent if it's a cylindrical body or if it's a planar body or if it's a sphere, the temperature profile is always of parabolic type with a zero gradient condition at the symmetry, so in the center, and then with a decreasing distribution in case of a source. And of course if we have a sink, it will be vice versa, it will be increasing. Which different boundary conditions can exist at the cylindrical surface? Basically we looked at two boundary conditions. They are nearly the same. They all prescribe a temperature at the surface. Once the temperature is directly prescribed by setting a value, explicit value for the temperature. The other case would be that we set the ambient temperature and we have a relation between the ambient temperature and the heat flux. Now, here I would like to also discuss what happens if we use and prescribe a heat flux on the body surface. Is this possible? It's the first question. And of course it's not, because the heat flux is directly known due to the integral of the volume, metric heat flux times the volume, and as such we will not yield any new information if we prescribe a heat flux. If the heat flux is different, we violate the steady state condition, and if the heat flux is equal to that value, we don't have another condition for the solution of the equation. Last question, how can the minimum and maximum temperatures be determined? For this we can use the equation that we have developed for the three different geometries, either set the location to the center where we know that this will be the maximum temperature, and we can also put it to the outside in order to obtain the minimum temperature. We can of course also take the derivative and check where this value is 0, but if we look at the part inside the brackets, we can easily see where this function will have a maximum. Thank you for your attention, have a nice day and see you soon.